Stir a spoonful of sugar into a glass of water, and within seconds, the crystals seem to vanish. But where does that solid matter go? The sugar has formed a solution, a perfectly uniform mixture. The matter is still in the glass, but it has been distributed evenly at a microscopic scale, rendering it invisible. A solution has a specific anatomy. First is the solute, which gets dissolved, like salt, making up the smaller portion. Second is the solvent doing the dissolving, like water, present in a larger amount. Solvent particles tear the solute apart into a perfectly uniform distribution. This microscopic integration transforms the solid into an invisible component of the liquid itself. We typically picture solutions as powders stirred into liquids, but the mechanics of mixing apply to all states of matter. Air is a gaseous solution. Nitrogen acts as the solvent, while oxygen and carbon dioxide solutes are distributed evenly within it. Solid solutions exist too. In a brass doorknob, zinc solute atoms are uniformly locked into the rigid copper solvent lattice. Despite these varied forms, liquid water remains the most effective solvent on Earth, capable of dissolving more substances than any other liquid. Water molecules have positive and negative magnetic ends. These charges allow water to latch onto and disrupt molecular bonds, pulling substances apart into the liquid. Drop that same salt into oil and nothing happens. Lacking magnetic charges, oil leaves the salt clusters intact and untouched. A solution only forms when the solvent's electrical charge matches the solute's chemical structure. Since water is such an effective solvent, it raises a question of scale. Can we add solute to a solvent forever? As you add sugar to a glass of water, the crystals break down and occupy the empty spaces between the water molecules. Eventually, the solvent reaches its saturation point. Every water molecule is occupied and bound to a piece of sugar, leaving 0 free molecules available. You can see this limit in action when sugar crystals stop disappearing and begin settling at the bottom of the glass, remaining solid no matter how aggressively you stir the liquid. Saturation marks the hard capacity of the solvent's microscopic real estate. These microscopic rules dictate the success of vital professional work in the macroscopic world. A pharmacist relies on the uniformity of solutions to guarantee safety. In an IV saline drip or an oral rehydration solution, every single drop contains the exact same ratio of salts to water. A chef manages the rules of immiscibility. Knowing that vinegar and oil will never naturally mix, they use a chemical bridge, like mustard, to force the two into a stable vinaigrette. An industrial chemist knows that water's ability to dissolve substances is a double-edged sword. It dissolves the oxygen fish need to breathe, but it can just as easily hide dangerous, invisible pollutants. They define the medicines we take, the air we breathe, and the fluids in our bodies. These chemical interactions provide the underlying balance for our environment and our health.